Okay, so we're going to talk about Taylor polynomials, and this is what, like, I know we went through all the series convergence stuff, and I know it felt like we were doing that for a long time, but this is really the meat and potatoes of the chapter. Okay?
So is this like the third course? He doesn't look like our right course, man.
So, what are the easiest kinds of functions to work with? Taking derivatives, plugging in values.
Polynomials.
Polynomials.
Trigonometry.
Polynomials are the easiest type of function to work with. Okay? Especially without our calculator. Right? So, basically what we're going to do is we're going to be able to take a polynomial and use it to approximate the behavior of a non-polynomial function. Okay?
So if we talk about natural log, it's going to be mean, not.
Okay.
We'll talk about Taylor.
So here we go. I want to approximate the behavior of the natural log of x plus 1 at x equals 0. Okay? So what's going to have to be true? Well, our polynomial at 0 should be the same as our function value at 0. Right? And this should be true for the first derivative and the second derivative and the third, blah, 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 to get a good approximation. Okay, so that's what we're going to go through. Are you ready? Here's the polynomial we're going to try to write. That's the function we're going to try to approximate. Okay? So our function is the natural log of x plus 1. What's our function value at 0? Okay. Which means in our polynomial, if we plug in 0, base of 0 is 0. Oh, we know one thing about our polynomial. Okay, so this is where we're going to go to, okay, so y equals natural log of x plus 1. Okay, so now we have, done, y equals 0. That's what we have so far. Okay, not a great approximation. Okay, so now let's go to the first derivative. Does everyone agree with the first derivative? Okay. Evaluated at 0, because that's where we're trying to approximate it at, is, so our first derivative at 0 is 1. Okay, now let's go to our polynomial. I want my first derivative to be the same as the first derivative of our function. So when we take the derivative of the polynomial, we get this, right? Which means when we plug in 0, we want a sub 1 to be 1. Okay. So let's go here. Now we have y equals 1x. Better approximation, right? Okay. Second derivative. Okay. Now, I'll save you some of the work. I know you can take a second derivative. Well, or we could think of it like this. Okay, let's not use the quotient. Okay. So what's the second derivative evaluated at 0? Excellent. Now, what happens when we take the second derivative of our polynomial? We have 2a2 plus 6a3x plus 12a4x squared. We're going to do this until we get a 4th degree polynomial. Okay? So, when we plug in 0 to this, the second derivative of 0 is 2a2. Which means okay. So let me go back to Desmos here. And our next function is y equals 1x negative 1/2, right? X squared. Ooh, look at that. We're getting closer. Oop.
It's like when you have two people.
Okay. Is everyone okay with what we've done so far?
Yep.
Okay. Just so you know, this is not going to be the process we have to go through every time. We are going to eventually see a pattern. Okay. Okay, so this is what we just did. Let's talk about the third derivative. Third derivative, positive 2 over 1 plus x cubed. All right, power rule. Which means evaluated at 0, we're at 2. Okay. Our third derivative for our polynomial, okay, we get 6a3 plus 24a4x, applying the power rule. And so when we plug in zeros there, we're just left with the constant. Therefore, okay, remember this is a constant, so when we plug in 0 here, it goes away. We're just left with this, and we want these to be equal. Therefore, the coefficient of x cubed is 2/6. Okay. Excuse me while I put this into Desmos. So now y equals x minus 1/2 x squared. It was plus 2/6, right?
Yes.
Okay, look at that orange. The black one. See? Okay. So now, last but not least, let's get our coefficient of x to the 4th. So we know that our 4th derivative is this. Evaluated at 0 is -6. The 4th derivative of our polynomial, 24a to the a sub 4. So when we plug in 0, obviously we're just left with the constant. We know we want that constant to equal -6. So our coefficient is -6 over 24.
Very nice harmonies.
Okay. Clever way of saying it. So let's go to Desmos. Will it let me cut? Oh. Okay. X.
If you do a Control C, it will let you.
Okay. And then we have to subtract what? And I'll change the color to red. Okay? So look at how with each value we added, we get closer of an approximation. Okay? So let's look at some patterns here. This is what we started with. Our polynomial, we wrote to be this. Okay? Now let's simplify it. You probably would rather write it like this, right? Okay, which, as Jared pointed out, is an alternating
What?
harmonic series. Okay. So let's talk about the form that this is in. Okay, so think about the numbers that we just came up with and look at those numbers in the denominator. Our denominators. 1, 1, 2, 6, 24. Not Fibonacci.
And
Wait, 1 times 2, 2 times 3, 1 times 2, 2 times 3, 6 times 4.
Or 1 times 2 times 3 times 4.
Oh my.
Oh,
Holy egg.
factorials. Egg. Okay. What are those numbers in the numerator? Look at what we used as we derived each of those.
N minus 1.
Look at all of the work we did with our derivatives. What are those values? What are 1, -1, +2, and -6?
Oh, just
N squared plus
0. 1. -1. 2. -6. Okay. So here we go. Our polynomial has this 4. Or this 4. Okay? This pattern is going to occur no matter what the function is. So let me go ahead and give you a definition. Okay? I know that you're going to write this down. But as you do it, write it down as a Maclaurin series.
what does that mean? Not Taylor.
It's a series generated around x equals 0. It is centered at x equals 0. Maclaurin series is a special Taylor series. If it's centered around something other than 0, we call it a Taylor series. So there are your two big bands.
Just like a Leibniz thing with both these guys working on the same thing at the same time, with different parts of the world.
That's a good question. I actually do not know the answer. So to actually write one of these series, we need the derivatives at each point, and then the factorial goes underneath. Okay? So if we want a 4th degree polynomial, we're going to take derivatives until we get to the 4th derivative. So we know it's always going to follow this pattern. Because we can do what we did with that natural log function to other functions, but we're going to get the same patterns. Where every time you take the derivative, that power rule is going to repeat until we get that factorial. Okay. that x to the fourth, we kept taking the power rule until when we got to the constant, it was 4 times 3 times 2 times 1. Okay, that's why that happened. So that's why we're dividing by those factors. If it's not centered at 0, we call it a Taylor series, and we do the same thing. Just notice that instead of x squared, x cubed, we have to write x minus a squared, x minus a cubed, because it's centered there, okay? So if we plug in a, it would go to 0. Like, we approximated the natural log of x plus 1 at 0. Anywhere else it doesn't approximate, but around 0, we were like, bang, right there. Okay? But at x equals 1, they were here. So if we wanted to approximate it at x is 1, then we would do this, and where x is 1, we would have all of those, that polynomial would fit right very nicely with the
So when we're writing one of these, we're going to have a point of 1 somewhere around.
Yes, and that's where we're approximating it, polynomial. Yes.
So, you could say we're approximating to the end, or are we ever going to approximate as n approaches infinity?
Yes. Okay. Example, y equals the cosine of x. Oh, come on, these derivatives are nice, people.
Does that mean they get worse?
There's some that aren't enjoyable. I mean, there's some that are tedious. I'm not gonna, I'll be upfront with you. Okay. So we are going to write a Maclaurin series here. A Maclaurin polynomial.
All right.
Okay.
Like,
Here we go. Our function is cosine of x. F of 0?
1.
Okay. First derivative.
Sine of x. Negative sine of x.
Sketch. Hold on. Some people write these down.
Yeah.
The first derivative evaluated at 0 is second derivative.
Negative sine of x.
Negative cosine of x. And if we evaluate this at 0, we get
Negative 1.
negative 1. Third derivative, Alex. Positive sine of x. Evaluated at 0. 0. Are we seeing a pattern?
Yes.
Okay. The fourth derivative is going to be negative, excuse me, I don't know why I said negative. Positive cosine evaluated at 0 is a positive 1. So this is going to keep happening. 1, 0, negative 1, 0, 1, 0, negative 1, 0. Okay. Let's talk about our polynomial. Oh, yeah. Okay. So our polynomial. We have 1. Yes.
Your notation, like with all the apostrophes, you just wrote 4 up there.
Once you get to the fourth derivative, you write the number.
Okay.
Yes. Yes. Okay. So we have 1 over 1 plus 0 over 1x. Now what's 0 factorial?
1.
1. What's 1 factorial?
1.
1. So your first two terms are just going to be the derivatives because they're dividing by 1. Okay?
0 factorial 1.
I'll answer that in the last minute of class. Okay? So then you have derivative over 2 factorial, third derivative over 3 factorial, fourth derivative over 4 factorial, fifth derivative over 5 factorial, etc., etc., etc. Okay? The way that I keep things straight, the factorial is always going to match the degree right there. Okay? And obviously that derivative is going to match up too. So this is third derivative, x to the third, 3 factorial. Okay, so what are we going to have? We're going to have 1 minus 1/2 x squared plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. We're only going to have the even ones, right? And this will go on forever. And we'll have a way of notating this later. Okay.
You could write a series.
Just have to read and see.
Okay. I'm going to give you another graphical example because I just think this is so fun. Okay. Once you have this written down. Okay. I will tell you these problems will take up a little bit of space because you have to go through all the derivatives and evaluate them and then write your polynomial. Okay, but the process isn't right. Okay. So let's look at the graph. Here's cosine. 1 minus x squared over 2 factorial. Add another term. Add another term. Add another term. Add another term. Isn't this cool? Like, look, like you can't even see it because it's approximating it so well. Okay? I just think that's pretty cool. Okay. Now, what's really cool is that we don't always have to like start over. We just wrote a polynomial for the cosine of x, and we'll get into more of this next week. But if I want the cosine of 2x, all we would have to do is plug in 2x for all of our x's, and we have the same, and we have that polynomial.
Whoa.
Okay, we won't use that very much today, but we'll use it quite a bit next week. Okay. Let's look at a Maclaurin series quickly. Let's look at cosine centered at pi over 2.
You mean Taylor series? Did we just look at them?
Yes, yes, I messed that up. This is a Taylor series. Excuse me. Okay. So we're going to center this around pi over 2, which is a nice number, isn't it?
Yeah.
So good to me.
Okay.
It's irrational.
What?
What's the cosine of pi over 2?
0.
Okay, so that's where we're starting. Then we have the first derivative is negative sine of x, evaluated at pi over 2, negative 1. Okay, so Jared has made a comment. We're only going to have the odd degrees because all of our evens are going to be 0. Okay, you guys have had calculus long enough to see what's going to happen here. Okay, our second derivative is negative cosine, and when we evaluate that at pi over 2, we get 0. Our third derivative is going to be positive sine, and when we evaluate that at pi over 2, we get a positive 1. And then when we get to the fourth derivative, we get back to the beginning of our pattern. So we can see that these derivatives evaluated at pi over 2 are going to go 0, 1, 0, excuse me, 0, negative 1, 0, 1, 0, negative 1, 0, 1. So let's write our polynomial. Now remember, this is centered at pi over 2, and so we have to write the x minus pi over 2 with our power. So here is, okay, our 0, f of 0 is 0, or excuse me, f of pi over 2 is 0. Here is our first derivative times x minus a to the first, plus our second derivative over 2 factorial times x minus a to the second. plus our third derivative over 3 factorial times x minus a cubed. Okay, so like Jared said, we're only going to have the odds. Okay, and this is how I would want you to write your polynomial. Okay, I am fine right now with you. If you write them as factorials or not, it's whatever. Okay, sometimes you're going to be able to simplify. Okay, but right now if you just keep them as factorials, that's fine. Okay. Eventually you're going to be able to remember some patterns, and there's going to be like 4 or 5 of these that you'll want to know by heart. And I'll tell you more about that next week. But let's get some terminology straightened out. When I say, I've been using some different ways of saying things. Okay. So here's a polynomial. This polynomial has 3 terms. It's a 4th order Taylor polynomial because it was found using the 4th derivative. It is a 4th degree polynomial because its highest power is x to the 4th. Okay, so if I were to talk about the 3rd order polynomial for cosine of x, it's only a 2nd degree function. Okay, and that's happening because the 3rd derivative is 0. So just because it's a 3rd order doesn't mean it's a 3rd degree function. Okay, so your homework, and then I'll tell you about why 0 factorial is 1. Page 644, 1 through 4, 13 to 29 odd, and 41. Yes, just writing these. Okay. So I don't think I gave you an overwhelming amount of problems. Okay, so what I want you to do is I want you to write them using all of the factorials, and then I want you to write them simplified. So I want you to write it 2 ways. I want you to write them with the factorials, and then I want you to simplify them if you can. So if you have 2 over 3 factorial, I would want you to simplify that down to whatever over 3.
1.
Yeah.
Okay, well, I mean, it's going to be like x cubed over 3 now. Okay, so let me stop this, and we'll spend the last couple minutes talking about 0.